So here we go. This is spectrometry for biology and chemistry. Here are the things I'd like to cover today. My goals are to show you the most commonly used investigations in biology and chemistry, and even a little physics at the end here, with looking at solution transmittance and absorbance in our wireless and UV-Vis spectrometers, also solution fluorescence with the wireless Vis spectrometer. Solution concentration, that's doing a Bayer's law analysis, figuring out the concentration of an unknown concentration using that relationship between absorbance and concentration. Time analysis, so looking at the change in concentration of a reactant over time to determine reaction order. So how do you do kinetics with the spectrometry software? And light analysis, looking at emitted light and determining where is the highest emission, where are the where are the highest emitted wavelengths in a source, an emission source. So I want to very briefly point out, I'm going to go, I'll be using the wireless spectrometer, which mainly covers the visible wavelengths and a little bit of the near infrared region, which comes with 10 polystyrene cuvettes and an optional fiber optics cable. That is part number PS2600A. Roger will put the link to that product in the chat, and I'll be demonstrating how to use that. That's the one that looks like this. So this is the Vis spectrometer. And then on the right side here, the UV-Vis spectrometer comes with 10 semi-micro cuvettes, which are more chemically resistant than polystyrene, and they can read lower into the UV, but not as far down as a quartz cuvette. So the quartz cuvettes are optional accessories. I think I have some here. So if you're doing analysis in the very short wavelengths, I might have said low earlier, I meant short wavelengths in the UV region, like in the 200s, you want the quartz cuvettes. But these semi-micro are good in the into the 300s and into the visible range. There's also an optional quartz excess fiber optic cable that comes with the UV-Vis. Often I'm asked, are the cables interchangeable between the spectrometers? And the answer is no. You would want to get the fiber optic cable that goes with the spectrometer pictured up here. So the UV-Vis spectrometer part is SE3607. Okay. Now, the spectrometry app, that's the software that you need to run the spectrometers. It's free. How do you get it? If you're using an Android tablet, you go to your Google Play Store and download it for free. If you're using iPads, you go to your App Store, Apple App Store, and grab that app. And Chrome OS, Chromebooks, go to the Chrome Web Store to get the app there. If you've got a Windows or Mac computer, then you'll want to go to pasco.com/spectrometry, and I'm going to drag that window over. So here I am. I'll move this out of your way in a second, but here I am at pasco.com/spectrometer. It'll take me to this URL. So here it's all about spectrometry software. But if you go over here to the right where it says downloads and click there, there's the download file for Windows computers or Mac computers. And there's also that information again on how to get the software on your other devices. Okay, let me move that back. You could also use the Spark LXI2 data logger. That is also compatible with spectrometry. So let's get started here. Without further ado, I'm going to open up the spectrometry app and I'm going to bring it over. It looks like this. So that's why I have this screenshot over here. One thing I wanted to mention, that if you're using a colorimeter, the colorimeter also is a way to study solutions with light, but it only has specific wavelengths that you can look at solutions with. So maybe you've got something interesting happening at the 475 wavelength. You might capture a little bit of that activity, but you can't get specifically 475 because your colorimeter only reads or does analysis at the 450 and 500 nanometer wavelengths and 550 and so on. If you have a wireless spectrometer or UV-Vis, you can get continuous wavelengths throughout. If it's the wireless Vis spectrometer, you can get throughout the visible spectrum and then even in some of that near infrared there. So what can we learn about a solution just by shooting some light on it and seeing what comes through on the other side of the spectrometer. Let's real quick talk about this color wheel. This is the Roy G. Biv wheel. And if you look at the diagonals, you're looking at complementary colors. So orange and blue are complementary colors. Red and green are complementary colors. And if I'm looking at what does that mean if I'm looking at a blue solution? Okay, so if I'm looking at a blue solution, I'm seeing blue. How does this instrument help me interpret what's happening with light? Now I'm going to bring over that application. So this is the Spectrometry app. Here's what it looks like when you open it, but actually what happens when you first open it is it does this. It says, hey, you don't have anything plugged in here. We've got to get a spectrometer on here. So I'm going to first demonstrate, and I'm going to switch my camera over to our spectrometer, the visible spectrum spectrometer. This one is a Bluetooth 4 version of the spectrometer. There's two ways I can tell that. First of all, if I look on the side, I see a 6-digit ID code. And if I look at the bottom, there's no ID code down here, no sticker to tell me any other information about its ID. So I see this. So that's my first clue that it's a Bluetooth 4 version of the spectrometer. The other way I can tell is when I try to pair it or when I try to connect to the software. So if I turn on my spectrometer, I turn it on, and now that Bluetooth light is flashing, so it's searching for something to connect to. I'm going to select choose wireless interface. And I see that there are two 5-digit codes on here, and then this 6-digit with a dash in the middle just popped up. That tells me that's my Bluetooth 4 version. These other two here are the classic Bluetooth versions, which you have to pair through the system settings. However, if you have the Bluetooth 4 version, oops, it just turned off. If you have the Bluetooth 4 version, then it shows up here. And I can just pair in the app. I select it and I click connect. And I wait for it to connect. If I was trying to connect another spectrometer and I don't see it listed here and it was on, then maybe it's classic Bluetooth and it hasn't been paired through the system yet. I'll go over that in just a second. So now I can see that this spectrometer is connected. I've got the hazard sign just turned into this infinite circle. So I can start doing analysis here, but instead I'm going to switch over to a different spectrometer so I can continue talking about the difference. How do you know which one you have? Okay, so I'm going to go to the connection and I can actually disconnect from there. Or I can, better yet, see now it's trying to find another spectrometer. Better yet, since I'm switching technologies, I'm just going to close down that app and start a new and turn off that one with the 6 digits. Okay, so this is my Bluetooth 4 version. Here is my classic Bluetooth version. How do I tell? First of all, I don't have a 6-digit number on the side. Second, when I look on the back, I've got this 5-digit ID number with no dash. And third, when I turn it on to connect, let me turn it on, I get the same Bluetooth light flashing, searching for something to connect to. But when I open my app, let me drag that back onto the screen. When I open my app, I'm going to choose my wireless interface and pick the number that matches the ID on the spectrometer. That happens to be this one right here. And I click connect. And again, if it's classic Bluetooth, you would have paired through the system settings prior. And like this is connected now, I can see that I've got my infinite loop here. Okay. Before I move on, I'm just going to check in with Roger. Roger, was there anything that we should go over out loud?
Nope, someone just asked a little bit about.
Okay.
So I just had one question about the colorimeter, and I'll answer that in the questions.
Okay, then. We're going to move on. Now, I wanted to talk about that blue solution again. Let me grab that blue solution. Here it is. So looking back at the color wheel, my solution's blue. I talked about complementary colors. I bet you there's something to do with orange here, since orange and blue are complements. Let's take a look at the software and see what I can determine about the relationship here. Let me start recording data. Oops, the software tells me, wait a minute, you need to calibrate the spectrometer. That's the very first thing you need to do when looking at solutions, you have to calibrate because I need to cancel out all the noise from the cuvette and the solvent. And this is my blank. And a blank is just a cuvette that has your solvent. I use distilled water to make all these colored solutions that I'm going to look at. So all I have is plain distilled water in here with no food coloring. And by the way, these are food coloring solutions. So my solvent is the blank. I'm holding the cuvette by the lined sides so that the clear sides stay clean. I would have wiped with the Kim wipe to make sure it was clean before I began, and I've already done that. So I'm holding by the lined sides, and I'm going to orient the cuvette into the spectrometer in this direction where the lined sides are facing this way and the clear sides go that way, because as the figure on the spectrometer tells me, my light source is here. Light has to go through the cuvette this way and to hit the detector over here so that I can see the spectrum. So that's how I orient the cuvette. And now to calibrate dark, I just click the button calibrate dark. That means the light's off. What kind of light's getting through? So it's going to eliminate any of the background light that's coming from my overhead lights here. And then when I calibrate reference, now the light's going to turn on and it's going to see what does it look like when light goes through a cuvette that is made of polystyrene that has just water solvent in it, and it's going to cancel all that out to get the baseline. And now now it's actually going, it's running, it's collecting data. I can tell because I hit record and it made me calibrate. And I've got a stop sign, meaning if I want to stop collecting data, I can hit stop and it'll record my signal. Right now it's flat 0 and my absorbance is here on the y-axis. And it should be 0 because I've canceled out everything by doing the calibration. So let's look at that blue solution now and see what's absorbed. Okay, absorbance. Let me scale here, this button down here with the X, looks like an X, helps me scale to full screen. I can also manually scale if I want on the axis. I can move the graph over if I want using the hand tool. I can do the same to the y-axis, same thing. I'm just going to auto scale. So I can see them on peak here, and I'm going to grab this coordinate tool and drop it on the peak there. And I can read the absorbance down here and the wavelength up here in the box. I can see that my highest absorbance is in the orange, and my wavelength here is about 616 nanometers. So what do I know about that solution? Well, even without looking at that solution in the spectrometer, I can guess that it's blue, because if absorbance is high for blue, then that must mean, I'm sorry, if absorbance is high for orange, then that must mean that the opposite color on the color wheel, the blue, is what's being made going through the solution. Let's see, going through the solution, that means transmittance. Okay, let me scale. And transmittance means that's the light that actually makes it through the solution and makes it to the detector. It's high for blue, and also over here. But I got a peak in blue, the solution is blue. What I'm looking at is what's transmitted. What is absorbed? Well, it is the complementary color on the color wheel. So you can make a prediction now about other solutions knowing that. I'm going to switch back to absorbance, and I have this neat tool on the far right. If I turn on this tool over here, I can look at transmittance and absorbance overlaid at the same time on my graph. And this will help explain to students what is the relationship between absorbance and transmittance. Well, if one's a peak, the other's the opposite, is a trough. Okay, so I'm going to stop collecting here because I want to keep this data, and I'm going to name the run. Instead of solution 1, I can click on here and hit the edit button and call it blue. It's blue food color. Okay, so now the next one I'm going to do is yellow. And let's make a prediction looking at the color wheel. If I'm looking at yellow, then what color is absorbed and what color is transmitted maximally? Looking at yellow. So maybe you think maybe violet is absorbed and yellow is transmitted because I see yellow. So I'm going to start collecting on my next run. I'm going to scale. And yeah, I see a lot of absorbance in the violet blue region and very little transmitted in the yellow region. And that's why I see that color. So I'm going to call this yellow. And finally, let's make a prediction about green. We've got green here. Let's take a look at the color wheel. Opposing color is red. All righty, let's get a run for green. And not quite red. It's not a peak at red, it's a peak at orange and a peak in the blue and purple area. Well, remember, blue has got a nice peak at orange, and what's the other color that makes up green? Yellow. Yellow and blue make green. So I've got a lot of absorbance over here in that violet, um, because it's this green color is actually made from a combination of food coloring pigments. So that's one way to look at solutions. It's a nice beginning way to think about what are the properties, what are the molecules inside of this liquid, what kind of information can we get from spectrometer. And if you get a run that you don't really want, like solution 3, I hit stop when the cuvette was out of the instrument. I can always select that run and hit the X to delete it and make sure that I really want to get rid of it, and I say yes. Okay.
Barbara, there was a question about, can you see more than one run at the same time? Can you see all the runs you make, for instance?
Great question. So I've got blue and yellow here. If I turn on this tool with the more than one line on it on the graph, yeah, I can see all the runs at the same time. And there's a color code here, that purple. It's a little confusing right now because the purple run is blue and the green run is yellow. So there is color coding. Purple, that's this run, that's my blue. This green run right here, that's my yellow color. So yes, you can look at more than one run at the same time. And you can also put more, if you have more than one peak, for example, there's multiple peaks on the yellow run, I can add multiple tools to get the multiple peaks there. And if I know what absorbance I want to look at, because let's say that this is a known compound and it's supposed to have maximum absorbance at 440, I can just type in 440 and it'll go all the way to wherever I type for that wavelength. Okay, any other questions we should go over, Roger, or should I keep going? Okay, all right, so now let me go back to the presentation. Let's look at some biology here, some spinach leaves. So let me switch. So right here, you can see that I've got some spinach leaves. I took the spinach and I let it soak in some 70% ethanol. And I crushed the leaves in that ethanol, and I made kind of a slurry of spinach leaves and ethanol, and then I filtered it with a coffee filter to get this extract of spinach. And now let's take a look at what kind of data I get when I look at this pigment, this green that came out of the leaf. So if I start recording, and this time I don't want to see all the runs. So let me hit stop actually and turn off all the runs. Delete the last one and start. And I'm going to scale. And okay, wow, look what I've got here. I've got this red orange and I've got this violet blue. Makes sense because my solution is green. But what also makes sense about this signature that you're seeing is these peaks are the peaks where the peak activity is of chlorophyll, of the chlorophyll pigment. So the solution that's green, it's chlorophyll among other pigments, but mostly chlorophyll. So over here, I've got chlorophyll A and B. A is a little bit more of a peak to the longer wavelength, and B is a little bit on the inside. And over here, I've got chlorophyll A and B, but also in here in the blue area, this is where my carotenoids would be, and my xanthophylls would also be over here in the purple, my yellow compounds. So I got a bunch of stuff going on here, and if I wanted to, I could separate out my pigments and analyze them individually. So I'm looking at a nice combination of all the things, the photosynthetic and protective pigments you'll see from a spinach leaf, just like that. So one other thing we can do with chlorophyll is look at what it does when it absorbs light and its photosystem is broken. I'm going to go to that in a second. And I wanted to point out this note here that says Experiment Library Plant Pigments. That note here, this is plant pigments. That's actually the name of a lab in our experiment library. So if you go to pasco.com, and if you go to resources, and you go to the experiment library, and you type in search plant pigments, that lab will come up, plant pigments and photosynthesis. So actually it's this one that says plant pigments. So I'm giving you the source for these investigations on the slides. Where did they come from? Look, this is what to look for in the experiment library, and it brings up the whole lab. And if you have a teacher account, you can get the student and teacher files for that investigation. So that's just a little bit of the plant pigments investigation. There's more to it, but that's just an introductory part. You could also do a qualitative analysis with the separation of pigments on chromatography paper. So here's a more separated by pigment diagram. Here is if you have a pure chlorophyll A run, that's going to be on the farthest extremes of the red and purple. If you've got chlorophyll B, that's over here, and the second peak in the red, and that's why we saw kind of one lump in the red region, because that's the combination of chlorophyll A and B, and same over here in the blue-purple region. And the carotenoids over here in the blues because of those orange compounds. And this sample I had didn't have, I didn't label the xanthophylls here, but here's the difference molecularly between chlorophyll A and B is this group here. Chlorophyll A and B have a single group difference, and that makes all the difference in what is their maximum wavelength that they're going to absorb, and what part of the solar spectrum can they use to convert energy, light energy, into chemical energy. Some extension ideas with pigments. I'm just going to list them here. I'm not going to name them out so we can save time and just move on to the next thing. But this picture here shows one of the example extension ideas. Got two different leaves. One was green, one was purple. Which is which? This is a fun thing you can do with students. Have them figure out what data goes with what phenomenon, or what what item you're looking at matches the data. So you can always go back and look at those ideas. So that's great. We can get all that information from solutions with color, but what do we do when you've got two solutions that have no color? For example, I've got, pardon my reach here. I've got this clear solution and this clear solution, and all I know is they're different from each other. That's it. How do I tell what they are if I don't have color to guide me as to what might be going on with what energy they're absorbing? Well, in that case, I would need the UV-Vis spectrometer. So I'm going to disconnect, or actually I'm going to leave the spectrometry, because again, I'm switching technologies. Now I'm going to go to a different spectrometer. I'm going to go to a UV-Vis spectrometer. I'm going to close out of SparkView. If I wanted to save my file, I absolutely could up here in the top left. I could do a save or a save as. I could also open a file, an existing file from here if I wanted to, and I can close the software from here. I don't need to save, I'm going to discard. Now I'm going to turn off this spectrometer and switch to my UV-Vis spectrometer. And it's been on, it's been running. You should let it warm up at least 10 minutes. And now this one plugs in via USB. So I'm going to go into my spectrometry app and bring it over so you can see and expand it. And while you're watching on the screen, I'm going to plug in the USB cable into my desktop computer here. It's going to take me a second to reach it. And I can't reach the plug. There we go. And it's just connected now. So the UV-Vis spectrometer connects via USB. It is not available in wireless. It's got kind of a lot of information that it's sending out, because it reads this range of wavelengths. By far the widest range of wavelengths we have on the spectrometers is the UV-Vis spectrometer. We can read into the UV. So that's how I can use that spectrometer to look at colorless, or a colorless solution, and know a little bit about what's going on. Maybe it absorbs in the UV region, and maybe that's how I can determine the difference between it and other compounds. So let's look at these unknown substances that I have here, and I'm using quartz cuvettes because I know that I'm going to be reading down in the UV, and who knows how far down I have to go in the UV. So I've used all distilled water as my solvent. And I just realized right now that when I was showing you the chlorophyll from the spinach, I had forgotten to say something important. I should have recalibrated with ethanol. because ethanol was my solvent. And I just wanted to mention that now. Oops, I forgot to calibrate with my ethanol solvent. I still got the right pattern of data, but I would have been better, even more accurate if I had recalibrated with my ethanol solvent. And that will happen again where I have to recalibrate, and I'll show it. So again, every time you have a new solvent, you have to recalibrate. So here we are. This time it's distilled water. That is my blank. So I've got frosted sides on this cuvette. And again, I've got the figure on the instrument to remind me how to orient the cuvette. Here's the light source. There is the receiver. So the light goes this way. I can hold the cuvette by the frosted sides and make sure the light goes through the clear sides of the cuvette and calibrate. Calibrate my blank. Just like that, we are calibrated. Okay, now I've got these two clear solutions. They don't have any color, totally clear, totally colorless. So I'm going to stick solution 1 into the spectrometer, and here's what I see. Okay, first of all, let me tell you a little bit about the absorbance range of your solution. So right now I'm not going to do any quantitative analysis, so I'm fine being a little high on absorbance. But if you are going to do quantitative analysis, which is coming up in kinetics, make sure that your absorbance is between 0.1 and 1.0. You don't want to go above 1.0 or too much below 0.1 because you start to get inaccuracies there. Your data is only most reliable in the range of 0.1 to 1.0 on your spectrometer. But in this case, all I care about is, what is the substance? I just want to identify it. It's qualitative and at that point. And where are my peaks? As long as I can see peaks and no flat lines up here, I'm good. If I do see flat lines, I can just dilute my sample with my solvent until I get into a lower absorbance range and eliminate the flat lines in my data. Now I've got a lot of wobbliness in my data here. How do I fix that? I've got options here. I can increase the smoothing. And you can see that improved it, but I still got a little bit of dancing here. Well, I can increase the number of scans to average. So what you might notice, okay, so my data got more stable, but what that's doing is it's taking more runs at a time on a rolling and doing a rolling average and smoothing it out that way, but it's also reducing the absorbance a little bit. So there's a little bit of a price to pay to use these tools, but it's up to you to decide what's the balance of cost benefit there. I usually find this a little bit's good enough to really study my data. So here's my solution number 1, and look what run 1's called. It's pretty called solution 1. So I'm going to hit stop. And what I can do to identify this is look at the maximum absorbance on one or both peaks. And this happens to be acetylsalicylic acid, which does have a peak around here. So hey, maybe that's what my stuff is here. Well, let's see what solution 2 is. Totally clear also. Totally no color. Let's take a look. And whoops, I did that really fast on accident. Let me redo that run. I double clicked my mouse instead of single click. There we go. So there's my next one. Oh, this is definitely a different substance. I got a totally different curve. Notice how I kept the settings I did for solution 1, so I have more comparable data. And now I'm going to move over to that peak. I've got one at 256, another one a little lower there, the 240s. And I can use these peaks to identify what is the substance. And it's definitely different than solution 1. And if I hit stop, I can make the comparison that way, and I can move my tools out of the way. Some more tools I can use on the graph. I can add an annotation with this letter A. And what that does is it puts a box, and I can put a note here. Maybe I say I diluted this one, whatever I want on my note, and I can move that to whatever point is appropriate. That kind of doesn't make sense for this data, but you get the picture. And if I don't want it, I can always hit the X. Same thing with the coordinate. If I don't want it, I can hit the X. Okay, so this rainbow icon gets rid of the background on the visible spectrum. So it's just, it helps point out where is the visible spectrum. It's not necessary though to do analysis. Sometimes it might just be in your way, especially if you have a peak like a yellow and you're trying to see where is that peak and it's hard to see, you can just turn off the color background. It makes it much easier to see your run. Okay, so that's pretty much all the tools here on the x-axis, but I haven't really gotten past this analyze solution page. There's 3 more tabs to look at here, so more tools to come. Let's move on to some more solutions here. I have some other stuff I can look at with UV, and that is I can tell the degree of saturation of a compound. Let me move to the next slide. This molecule up here on the top left and this one on the top right, both of them are 18 carbon chains. Both of them are fatty acids. Both of them have this carboxylic acid at the end, so you can see they're fatty acids. And you can look at them and you can see which one is less saturated if you're looking at this structure. I've got more double bonds here, so I've got less saturation. I've got only one double bond here on the left here, so I know that this is more saturated. This one is monounsaturated because there's only one degree of not saturated here. And then this is poly. I've got a couple double bonds in the molecule. Well, how does that look in my spectrometry data? Let's see. And which one might have which shape? So I had already calibrated with water. If I wanted to, I could calibrate with hexane, but I'm going to keep water in there. Now I'm going to look at olive oil. And this is straight out of the bottle, so I'm not too worried about the absorbance being over 1. I'm just kind of want to see what's the shape, where are the peaks, and compared to other oils. So I'm just going to rename this run olive oil and see what I can learn about the structure of olive oil compared to soybean oil. So this next one is soybean oil. Let's turn on multiple runs, and I'm going to get rid of the first 2 runs since they're not relevant to this data set. And I can see definitely something interesting in this comparison. All right, I've got the soybean, which is the green run, is farther to the right, closer to the visible spectrum. Olive oil is farther to the left, closer to the UV. And I also can see, look, there's chlorophyll in my olive oil. There's those peaks from the chloroplast, right, in the red and violet region. I've got chlorophyll there. Nice. That means this is nice, fresh olive oil. So let's take a look at those molecules in the presentation. If we look, let me move this over here. If we look at these 2 molecules, we can see that the less saturated one, this one, that's olive oil. This red one right here, that's this one with only 1 double bond. The one to the right, soybean, by the way, this is oleic acid here, this fatty acid. And the one on the right, this fatty acid is I always struggle with the name, linoleic acid. Is that right, Roger? Linoleic. And it's got 2 double bonds in it, so it's slightly less saturated. And that the less saturation you have, the more the spectrum will be shifted towards the visible. So if that's true, I've got this third oil sample here, which is canola oil. And oils are a mixture. They're not just one fatty acid, they're a mixture of fatty acids. Canola oil has both of these fatty acids in it. Let's see if we can figure out which of the fatty acids it has more of. Does it have more of oleic or linoleic? Or cannot remember how to say it. Let me start and let's see. So here's my canola oil. Let's show all the runs. It's right there in the middle, but it's shifted closer more to the right. So then I can know that I've probably got more of this fatty acid than this fatty acid. And that's true. Canola oil is more of the this acid, this fatty acid, than of oleic. It does have both, but more of this less saturated fatty acid. And we can also tell it's less saturated because it's closer to the visible spectrum. So we get all that out of this UV-Vis spectrometer. But I'm going to switch back to the visible spectrometer in just a second. And while I'm setting that up, Roger, do we have any questions we should go over out loud?
Nothing in the questions area.
Okay. All right. So I'm going to turn on that spectrometer, and it's the UV-Vis spectrometer is cooling off, so you can still kind of hear the fan in the background. Now I'm going to go back to, again, I'm going to switch technology, so I have to turn off, close down spectrometry. Before I do that, I wanted to show you some tools up here on the right. I can take a snapshot of my data, and it goes into a journal, and I can write notes on it and save it into my file. I'm going to close it though, since so we can save time. This file, I can export data as a CSV file if I want to analyze it further in Excel, but when I show you the next tabs, you may not think that you'll need to export to Excel, but you can as a CSV here. And in the settings here, you can find out which version of spectrometry you have, or you can change the language, or you can go to our online help. You definitely want to see which version of spectrometry you have. I've got 250, which is the latest release. This is the version you need to have in order to use the Bluetooth 4 version of the software. So if you get the latest spectrometer with Bluetooth 4, you need 250. Okay, so you'll have to uninstall and reinstall. And again, follow those download instructions I gave earlier. So I'm going to restart because I'm switching back to the wireless. And actually, I need to unplug the USB so that it doesn't accidentally grab the spectrometer. And let me reopen this. By the way, on the if you're looking at my screen and you're wondering, why do I have crystal violet on here? We're going to do a bleaching reaction. And another thing you can look at with the UV-Vis Spectrometer, and this is the name of a lab that's on the website you can look for, conjugation and UV projection. Basically, if you've got a higher degree of conjugation, which means the alternating double bonds in the same plane in a molecule, it will change the way which wavelength is most absorbed. So here I've got less conjugation because we lost some double bonds when the crystal violet color disappeared, but I've got more here on the left side there. So check out that lab if you're interested in seeing how the degree of conjugation leads to which UV band a sunscreen can protect against, A or B. Okay, so now we're going to look at fluorescence. So I asked that question earlier, what do plants do when they still have chloroplasts, but you've busted up their photosystem and they can't send those electrons down to the electron transport chain and make chemical changes to produce different products. So in photosynthesis. So now I'm going to reconnect this wireless spectrometer. See which one this one is. This is, oh, there, you might have just heard my, you might have just heard the UV-Vis spectrometer turn off there. So I still have my cuvette in there with chlorophyll. So I'm going to connect that. Okay. And wait for that to connect. So here's my chlorophyll again. Oops, I have too many spectrometers on. Let me turn one off. Okay. All right. So I've got a sample of chlorophyll here, and I've got the ability to look at whether or not a solution fluoresces. That means I can shoot light at it and see if it absorbs that wavelength and re-emits the energy at a different wavelength. Okay, so this is like a emission. If I go to fluorescence, this is 405 nanometers. That's about the wavelength that is going to be pushed through the solution. I'm going to hit start, and I have nothing. I have no cuvette in my spectrometer right now. I'm going to use this tool called integration time. When I look at emission, I might need to adjust the sensitivity of the device to the light that's being sent to it. So I'm adjusting the integration time. And now you can really see the signal here peaking around 405 nanometers. That's because this, what you can see into the spectrometer, this light at 405 nanometers is like blue purple. It's exactly that wavelength. That's why it's peaking right there. So with nothing in there, I see where 405 is at. If I put in my chlorophyll solution, it shows that, oh yeah, chlorophyll that's able to take 405 nanometers and absorb it and re-emit it at red. So if I look into my colorimeter, you can kind of tell, look, it looks red now. My solution's all red. That's because my solution is actually re-emitting the energy as red energy. How do I know this is emission? I look and I see that it's red, and I also look here, and this is actually intensity, not absorbance. Red went up because it's shooting out red photons, absorbing these violet photons, shooting out red photons. So this is what plants do when you break their photosynthesis and they're stressed. They can't send those electrons that you shoot out, the light energy you give them, they can't put it through their photosystem. So they just emit as red light. And you can actually see that from space. It's something that scientists can do. So that's what 405 nanometers looks like without. And if something does not emit at that wavelength, here's what happens. This is just water. Yeah, it just dropped because the cuvette's there, it's blocking the light, but it's still at 405. I didn't shift my wavelength at all. It just dropped in intensity, meaning it's not absorbing and not re-emitting light at all. Where this one, this is the spinach, is absorbing at 405 and re-emitting at a red wavelength, and that's why I'm seeing red light come out of my solution now. Okay, so that's fluorescence, and that's on our wireless spectrometer. There's also a 500 nanometer wavelength. But now I'm going to move on to concentration. I got a warning again. It's saying before I analyze the concentration, I have to go to analyze solution. Okay, here's what that means. Go to analyze solution. I'm going to take that blue food coloring we had earlier, and I'm going to do a Beer's law analysis to see if I can figure out the concentration of an unknown concentration of blue food coloring. So I took the blue food coloring and I diluted it into a few different concentrations. I'm going to set the first concentration. Oops, I still have fluorescence on. I need to go back to absorbance and transmittance. Okay, so I've got my blue solution in there, and I need to actually, the first thing I need to do, remember, calibrate, always calibrate. So let me find a cuvette of distilled water. Everything is made with distilled water for my blue food coloring solution. So I'm going to calibrate dark and then calibrate light. And that was pretty painless. We're ready to go. Now I'm going to put in my blue food coloring solution, and I have to pick a wavelength to analyze at. So now that I'm doing quantitative, I definitely want to keep my eye on absorbance and make sure that that I've got the absorbance below 1, which I do. Okay, so I have to pick an analysis wavelength, which means I have to move my picker, my wavelength picker, and hit the check mark on there. And I'm going to see this black line come up and show me what wavelength do I want to look at when I'm analyzing blue solutions. Well, that's where the maximum absorbance is, as long as it's below 1. So if I was doing, maybe if I was doing copper 2 nitrate, maybe I get a signal that looks like this. It keeps going into the red and it just flat lines up here. As long as you've got something below 1, use that as your analysis wavelength, and you can analyze your solution, even if it's flatlining back into the near infrared. So I'm going to analyze at the orange wavelength, and now I'm ready. I've got 617 orange, my max absorbance picked for an analyzing concentration. My concentrations are editable here. It's suggests to start low, go high. You can do that, or you can go high to low. Just go in order. It doesn't matter which direction you pick. So my first concentration is 1 molar. My next is 0.67 or 667. Next is 0.50, 0.333. And finally, I'm just going to use my blank to say 0 concentration. And if I hit start, recording, this is my 1 molar solution, and I wait for it to stabilize. I'm going to keep the value. I do the next concentration, the 0.667, wait for it to stabilize, and you'll see that the graph is building as I go. Next solution. Great, next. Okay, and finally my distilled water, which should give me a 0 absorbance. Great. So I've got this graph, and let me expand it to full screen. See these dots? That looks like a linear relationship, but just to make sure, I can turn on, now I have different tools down here. I can turn on my linear fit tool, and Beer's law says that absorbance and concentration are proportional to one another, and they are. I can see I have a nice straight line and a good fit. My R value is very close to +1 because I've got this increasing as concentration increases, so is absorbance. My slope M is 0.828. My y-intercept B is very close to 0. That means it's almost going exactly through the origin. This is definitely a good linear relationship. So I can use this calibration curve of known concentrations of blue food coloring, or if you're doing copper 2 nitrate, same thing, just put the molarities in, to figure out the concentration of this unknown solution. So if I start recording again, and I put in my unknown solution, I want to do that down here in this special area for determine unknown concentration. I've got an absorbance of 0.123 or 2. I'm going to keep that value, and it doesn't show me that on the graph because this is to help me figure out, well, if I've got absorbance here, 0.124, how do I know what the concentration is? There's a few things I can do here. I can move my graph to where I think 0.124 is, and I can adjust my scale to get 0.124 to show up, and I can see where that linear fit crosses through the x-axis. So, okay, my concentration is probably around 0.11 or 0.12. That's one way I can do it. I can also use my linear fit equation, y equals mx plus b. So my y value, what is on the y-axis? Well, that should say absorbance. Oh, I can't see it. That should say absorbance. Let me see if I change the size of the screen, if that makes it come back, or change tabs. I have to hit stop too, that might help. Okay. All right, well, I'm going to close and reopen. When in doubt, close and reopen. And that's okay. Luckily, this was a quick to get data. We definitely want to see what's on that y-axis so that we can do kinetics, right? So let's restart, reconnect. Pick that analysis wavelength. First thing, oh, we have to calibrate. Okay, calibrate. There we go. And move on into record our analysis wavelength. And we'll keep that 617, move on to concentration, recollect my data. Start collecting. Yep, that was the same value as before. Next. Great, next. Okay, and since I'm going fast and not letting it stabilize, it's still going to be linear. It might not be as beautiful as the other one, but it will still be linear. And yes, we still have a really good fit there. Okay, so now I've got absorbance back on my screen. I was saying the other way you could figure out the unknown absorbance is by plugging everything into that linear fit equation. So if my y value, what's on the y-axis? That's absorbance. There it is. It says absorbance. My absorbance was 0.111 of this unknown solution. So if I use y equals mx plus b, I can plug in 0.111 for y. So 0.1111 is y. Y is equal to mx plus b. So the first thing I'm going to do, the algebra, is I'm going to subtract out that b value, 0.199, and then divide by the slope m, 0.823. And my value is 0.11, which, remember, when I pulled down the graph, it estimated as like 0.11 or 0.12. That is the mathematical way to determine the unknown concentration. And that makes sense because when I look at my unknown concentration, it looks like it's somewhere between the perfectly clear and the last blue. It's lighter than the last blue one, so it should be somewhere between those two values, and it definitely is, between 0.30 and 0.00, and it's 0.11. So that's how we do a Beer's law analysis. But the other good news is if you do a Beer's law analysis and then you subsequently do a kinetics reaction after you've gotten this concentration curve, you can, and you're using the same one of these concentrations within that range of concentration up to 1, absorbance of 1, then you can do your kinetics and it will know the concentration, not just the absorbance. It also will know the concentration. Let me show you how that works. Let me switch over to the time tab. Now we can look at absorbance over time. So what I'm going to do to get this reaction going is get my blue food coloring. And by the way, this is the 1 molar solution. I'm going to add a few drops of bleach. And we'll invert and start recording and see how that looks. And get that cap on, invert 2 or 3 times. You don't want to delay too much because you want to definitely capture the beginning of the reaction. I'm going to scale, and I want to point out some things while this reaction is going. Look at my analysis wavelength, which I picked way back long ago at 617. Do you see how this graph is dropping? I'm losing absorbance at 617. Well, what's going on? We can't see because I've got the cuvette and the colorimeter. While that's going, I'm going to repeat the reaction in a test tube. So here's some blue food coloring in a test tube. I'm going to add some bleach to it. And watch what happens over time. I've got some white tape behind the test tube so you can kind of see better what's happening. We're going to let this run for a couple minutes. And so far we've got 1 minute. I can detect the lightning blue. It's getting lighter and lighter blue inside the test tube. You might not be able to see it on the camera, but I can definitely see it. So that's what's happening in there. And in fact, it's already a lot lighter because it's been going longer than the one in the test tube. I can also see the shape of my curve is changing a little bit, it's starting to flatten out a little bit. So I can definitely see that the rate's changing with time. I've got some familiar tools down here. I've got a linear fit. I've got an annotation tool. I've got the coordinate tool. I've got the scale tool. I can turn off and on that background spectrum, which now we can see we've really dropped in our original absorbance value from the beginning at the analysis wavelength of 617. If I turn on this tool, it shows me what's the instantaneous time and absorbance. Toggle it off or on. And I'm just going to I'm going to stop it here. It's gone for about 2 minutes. So let's stop and let's do some analysis. And you can see that the test tube is almost totally clear now. It's really light. So doing the kinetics analysis, if I look on my y-axis, I've got absorbance. And I want to see which is the most linear. Is it absorbance over time? Let's turn on a linear fit. My R is negative 0.981, which looks like it might be a good fit because it's close to -1, but when you look visually, it's really not that great of a fit visually. So let's click the absorbance tab, and now, whoops, it goes to transmittance. One more time, and I go to concentration. How does it know concentration? Because we did this Beer's law back here. We told it how to figure out the concentration of a solution already. So now we can look straight up at concentration. We've got molarity here. We can get molarity over seconds for analysis here. So if we go to the quick house button, now this is just if I had a zero order, this would be the linear one. This would be my absorbance or concentration over time. Now I've got the Ln concentration or Ln absorbance. It's more linear. I've got an okay R value, but it's a better fit than the last one. Let's see. So this would be a first order reaction, right? The Ln. Let's see if maybe second order is a better fit. And nope, second order, which is the inverse concentration, inverse molarity over time. Nope, not a good fit. So my best fit is that Ln. That means this is a first order reaction. And now I've got my number to put in my expression. I also got my M, which is my rate. So I've got K, I've got the rate constant. I could also just analyze, if I turn on the box tool, I can analyze just the first 30 seconds and run my analysis off of that. Whatever amount of data you want to analyze. Like maybe you started the data collection before you even started the reaction, so you didn't miss anything, and you wanted to only analyze like 30 seconds in and going forward, you could do that with the selection tool. Okay, any questions we should address out loud, Roger?
Questions have been dealt with as we've been going along. So nothing that was something I could stop you to answer.
Great, thanks. Okay, so I'm going to skip past these now. Something I forgot to go over on the Beer's law. There is another built-in tool to tell you how right you were about your predicted concentration for the unknown. Mathematically, we thought that the concentration was 0.11. Let me bring my calculator back up. I got 0.11. Let me round to thirds. It looks like I have 3 sig figs up here. Yep, I can do 3 sig figs. So let's do 0.111 as a concentration. Wow, that's a nice coincidence. Oh, and look at that. It plotted this bright green dot for me saying, you're right, probably. And how do I know I'm right? Probably. Well, first of all, my value that I predicted is right there on the line. on my linear fit, and also because the software has this feature where if you get a bright green to green and before it turns green, you have a really pretty good error below 5%. Between yellow and brown, you've got within 10%, 5 to 10%. And if you got a red X, your error is above 10% or above. So if I really mucked up my concentration, let's do that. Oops, I doubled the concentration. I'm really wrong. I've got a big error, so it gave me a red X. But if I get in the ballpark, I get that brownish box. And if I'm just right, within 5% error, I get the green as go light. Okay, I am gonna do, I think I'll do the peroxidase last because that's going to take a second to set up. It's very similar to the kinetics study we did here with concentration over time. I am gonna get to it. I'm gonna do the analyze light because it's one more function since we're running out of time. And then I'll come back to the guaiacol, or rather the turnip peroxidase investigation. So I'm going to show you how you can use the analyze light tool to study, to figure out the unknown element in an emission bulb. So I'm going to move my camera a little bit. Let me zoom out. You can see my messy setup here. And you can see in the background, I got my Kim wipes and a bunch of stuff. And this is a emission tube of what element, I don't know. I can use the software to find out. So what I've got hooked up here is I've got a fiber optic cable. Here's one that's unplugged from the sensor, and I'm going to use the visible spectrometer to figure out what is the unknown element in this emission tube. So I've got that thing on, and you're looking at that, and you're like, I can tell what it is by the color. But let's use some quantitative data. I'm gonna stick this looks like a cuvette, and it goes in the cuvette spot, and there's a marking on the cable to show you what direction to point it in. I'm gonna start recording, and I'm gonna turn on that integration time tool again. I know we're running out of time, so if you need to leave, go ahead and leave. Don't, just we will send you the recording. So thanks for being with us. If you have to go, I'll continue. In the meantime, here are the peaks we've got for this sample of light. I've got 1, 2, probably. I've got 3, a little one over here, and I can't see. I've got some peaks here. Can't see anything past there. So I'm going to turn on this reference here on the right. Right now, there's no reference. I can cycle through these different elements and see, oh, there's the black lines. Those are the reference lines. It's definitely not nitrogen. It's probably hydrogen. And I've got a little bit of noise over here on the right side, but or left rather, because I've got good alignment on these other 2 peaks, I can be pretty sure it's hydrogen. But if I wanted to, I could move my entire reading with this tool here, the calibrate wavelength tool. So let's say it looks like I'm just maybe 1 nanometer off. Let's go to the left and see what direction that goes. 1.2, look, it moves it to the left. If I go to the right, it moves my whole signal to the right. So if I want perfect alignment on that first peak there, a little bit more, whoops, too fast. There we go. That's pretty good. Let me nudge it over to the right so that all of my peaks now are pretty well aligned with the reference. Got some noise here, but I'm pretty confident that this is hydrogen. So let me turn that off and come back in a little bit. And let me move to this presentation here. So we are going to come back to this kinetics for biologists with enzyme activity and plant pigments. One thing I wanted to mention is there is other instruments we have to study matter with light. We have the polarimeter, the colorimeter, and turbidity sensor. Roger's going to put a link in chat to get you to all the other sensors that use light to study matter. Contact your PASCO rep if you have any questions or you wanted to get in touch with customer service or teacher support. Just go to pasco.com/support. Roger's going to drop that link in chat. If you can stick around, go ahead, stick around. I'm going to do the peroxidase next. Otherwise, we'll send you the recording with the peroxidase activity in there. And I'm going to scoot back to that now. Roger, before I start that activity, is there any questions to go over?
Right. There was a question about the screen where you showed what the colors and the accuracy meant. Is that something that you made, or was that in the help file? Sure. You showed a screen that had those colors and what the percent accuracy breakdown was when you were guessing at the concentration. How did you get those values? Is that something in a help
Oh,
screen, or did you make that?
oh, I'm not sure which. Was it in the software? Or?
It was in your presentation.
Oh, go back to it. This one?
Yes.
Oh, okay. How did I get that? Well, that's just Thank you. This is just something I discovered by working and doing a percent error analysis because I knew what they were, what my solutions were, and I just checked what they were. You know what? I don't think